Hey all, today I'm just going to be making a video which is a geometric proof of the Pythagorean Theorem. So we've been going through the Pythagorean Theorem a little bit, or at the very least we're going to start doing that. And oftentimes students are fine with just knowing the formula c squared equals a squared plus b squared and how to use it to solve for unknown side lengths in a right angled triangle. However, some students, like myself when I was a student, really wanted to know why this works, and doing this proof geometrically really helped me understand the Pythagorean theorem and what it's saying, and showing that it's actually a real thing and you should trust the formula is going to work for geometric reasons. So I'm going to show you that proof that I learned today. So here I've got a right angled triangle and it's got side lengths of A, B and C. So no values, we're not going to use values at all in this. We can just do it abstractly using pronumerals. And I'm going to use this triangle 4 times in 2 separate squares to prove that c squared is indeed equal to a squared plus b squared. So to start with, I'm going to construct square number 1. So I hope you'll bear with me as I construct this square, or at least try and construct a nice looking square. It's a bit more rectangular than I would have hoped, but close enough. Let's pretend that that's a square. And I'm going to construct 4 diagonal lines here, which hopefully end up looking quite good by the end. We'll go to here, and then we'll go to here. Now it doesn't look perfect because I have drawn this on the fly. And what we're going to do now is we're going to take our white pen and we're going to label these side lengths. Now you'll hopefully notice that I've constructed, and I'll even color them in, I've got this triangle 4 times. I've got one there, one there, one there, and one here. And I'm going to label them as the short side length is A for all of them. So A, and A. And I've also got the long side is B. So B, 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 and B. And the inside side lengths are C, 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 and C. So the outside square, I need to establish one thing about it. I need to say that the area of the outside square is equal to side squared, as we know, which is going to be equal to, in fact, we actually don't know that this is a square yet. I've told you it's a square, but we haven't proved it yet. So what I'll do is I'll say this is certainly a quadrilateral, and it's certainly a rectangle because we're using right angled triangles in the corners. So we know all the corners are right angles, meaning this is at the very least a rectangle, but I can prove it's a square because I have length times width, which is going to be the length here. If I can draw a nice one of these guys. Oops, get my white pen. One of these. This is going to be A plus B. That's this side length. And likewise on the top, that's A plus B as well. So length times width here, we have A plus B times A plus B, which is just another way of saying A plus B all squared. And the fact that we have 4 equal sides means this is a square. So the area is A plus B all squared. Great. That doesn't prove anything yet, but I'm going to get to that. The second thing we need to do is construct another square. Okay, and it's going to be similar using the 4 triangles, but it's not going to be in the same orientation. You'll see what I mean shortly. I'm going to draw a rectangle to start with. And then I'm going to draw a diagonal line through it like this. Then I'm going to draw another rectangle. Which is, well, that last one was just not okay. It needs to go straight up. There we go. And we'll finish it off there. And just a diagonal bisector as well. So I'm going to label this configuration as well. Short side length A, long side length B, short side length A, long side B, short one A, long one B, short one A, long one B. So again, I've got my 4 right angled triangles that have side lengths A and B. And what we have to do here to notice that this is a square is we have to do a little bit of creative accounting, as they say, and we're going to draw hypothetical lines like this. So that's a right angle, and also hypothetical lines here, and say that that's a right angle also. And now we have another square, and I'm going to replace these inside side length dimensions and put them on the outside of my large square. So this side length I've just rubbed out, A, is here, that's A. Likewise, this side length A can become A up here. And likewise, these two side lengths of B can just move sideways, okay? And now we've got another square, because the area of this guy is again equal to length times width, which is going to be again equal to A plus B all squared, for the same reason as that last one was A plus B all squared, because these side lengths here are A plus B as well. So the key thing to note here is that both square A, square 1, and square 2 are both have the same area. They've got the exact same space. Not only that, but the space that has been actually taken up has been by the same 4 red triangles, meaning the space that is left over is equal, okay? So in my first triangle, I'm going to say that the area in here is equal to C squared, okay? Because it's C times C, so it's C squared. All the side lengths are C, which makes it a square, so the area is C squared. And I might even rub out all of those C's because that's a bit confusing. And likewise, the area in here is going to be B squared. And the area up here is going to be A squared for the same reason. And therefore, if both squares have the same total area and the area that's taken up by red triangles is exactly the same, then the negative space, if you will, is the same area as well. Therefore, the negative space here is C squared, and the negative space over here in total is A squared plus B squared. And we've just established that those two things are indeed equal, meaning that the square of the hypotenuse in a right angle triangle is equal to the sum of the squares of the two other sides. Or in other words, C squared equals A squared plus B squared.